So Bayesian classification methods, it has a solid foundation on Bayes theorem. And today we're going to first learn naive Bayesian classifier. And I think next week we're going to look at Bayesian network. This a naive Bayesian classifier has long been used as a benchmark. It's very, very simple. Actually, the model does not need to be constructed. The data itself is the model that you can just quickly classify new examples without constructing a model. And I know many earlier web search engines used naive Bayesian classifying tags. So it's a widely used classification algorithm, even though some of the assumptions is not met in the practice. Naive Bayesian classifier. So in this scenario, as before, we have D, which is a labeled set of tuples, and as their associated class label. Each observation is represented by an attribute vector. So here we have n attributes. So every x is a value to a specific attribute that describe one observation. And suppose those observations belongs to m different classes, so we have those classes. In naive Bayesian, classification is derived by computing the maximum posterior probability, which is given x, given this observation, what's the probability for this observation to belong to class Ci? Probability of Ci is the prior probability of how many times class I occurred in the training example. So from the Bayes theorem, we know that this value, this posterior probability, is equals to this. Because for a fixed data set, the probability of every x occurred is fixed. So we can ignore this because our goal is just to find the greatest value for a class. We're comparing the value of this term to find which class has the greatest posterior probability for observation. So then we are left only with those two things, and we know how to estimate this. We can use number of observations belongs to class I divided to total number of observations. That's our PCI, the prior probability for class I. Now we need to figure out how to find this. In order to do that, we
have a question on the,
sure.
The previous slide, where the P of x is a single observation.
Yes.
Correct. So P of x means, let's say I have 100 observation, then probability of x is 1 by 100.01, or does it mean something else?
Sorry, what was the question? So P of x, I know what you're talking about. P of x. Your example, your concrete example was
that I was wondering whether if x is a single observation,
yes,
then is P of x simply 1 upon the number of observations? Is that mean, let's say we have 100 observations, that means P of x is 1%?
You can think of that way, but really this factor make no difference at all in this in naive Bayesian classification, because our goal is to compare, because the probability for x occur no matter which class, it's fixed. The probability, this is the prior probability for x to occur, right? This is fixed no matter independent of any of those classes. So because our goal is to predict to compare which of this value is greater among all the classes. Therefore, we can ignore this.
I was just maybe wondering, and maybe it's
Oh, yes.
oversimplifying, why instead of P of X, why did they not just use N, divide by N, which is a constant which we can take out? Is it because that there's some difference, like instead of just divide by N?
Because Bayes' theorem says so. So Bayes' theorem is basically conditional probability theory. This is joint probability. So this is a joint probability of, this is one way of writing joint probability of C and X co-occurs. If you move P of X to this side, this is another way of saying the same thing. Therefore, you have this equation. In order to find this has to be moved. P of X has to be moved down here as a denominator, right? It has to be P of X. Only in this case, we can simplify the problem by ignoring it. Because we only need to find for this observation, should PCI conditioned on X greater than PC2 conditioned on X, which one is greater? If C sub I sub 1 is greater, then we believe X belongs to class 1. If C of 2 is greater, then we think X belongs to C sub 2 class. So now our question has been reduced to compute this term. How do we do that? It's very, very challenging. But if we apply a conditional independent assumption, then it becomes really simple. This conditional independent assumption is, if we know this class, then all the attributes are independent of each other. You know, when I was first learning about conditional independence, I found this concept really hard to understand. Something could initially to be dependent. Once you add a piece of information, that thing suddenly becomes independent. So I searched for examples, you know, under what situation that could occur. I found a good example that's easy to understand. Think about children. Children's height and their vocabulary size is not independent, they're dependent. You can see taller kids probably know more vocabulary. Like my daughter, she's in college, she's taller than my son. She definitely knows a lot more vocabulary than my 10 years old. However, if we add another piece of information, if we know the age, you know, among kids who are 10 years old, their height and their vocabulary probably are not that dependent anymore. So that's how I started to understand conditional independence. So here we say within this class, the attribute, different attributes are not dependent. If with that assumption, we can actually simplify this joint probability to a simple product of all individual attributes that are involved in this observation. So this gave us this formula. Okay. So we only need to count class distribution. We only need to count for this class how many observations has this value for this attribute. So that will give this give the values for every factors that we have in this equation. Now to estimate this probability, I just give one way. If A is categorical, counting how many times xi, A equals xi. But if certain attribute is continuous value, then what do we do? One thing we can do is to assume this attribute values are normally distributed. Then within one class, we can compute their Gaussian probability. That gave us the probability of giving this class, what's the probability for A to take the value of X. Right, so we can, for this class, we can compute the class average and standard deviation. And using this formula, we can find the probability, which is one of the terms here. Questions? Okay. So this is one example that we can, using, again, the computer buying data set to illustrate naive Bayes, Bayes classifier. So we have by computer, yes, not by computer, no. This is our model. And then the data to be classified is this instance. If age smaller than 30 years old, income is medium, student, yes, credit rating fair, will this instance be classified as buy or not buying? So first, using the, because we know we need to compute this value here. Therefore, we need to first compute the prior probability for CI. We have two classes, yes and no. And we have 14 instances, yes and no cases. We have a good estimate of the probability for the class prior distribution. Then we compute the second term. For each class, for yes class, we compute, because our example is age is smaller, all those attribute combinations, we end up need to have all those values, right? Yes and X. X covers all those 1, 2, 3, 4 attributes. So individually, we compute their conditional probability, and then we put them together. So for yes, buying, and X, so yes, we take out this, yes, take out this, another yes, take out that, another yes, take out this. And this gave us the probability for if somebody's buying the computer, what's the probability for us to observe this example or observation. So once we found that and this for the no class, we can actually compute this. Compare this to, we see that the first value is greater. Therefore, we classify this instance as a computer buyer. Buy computer equals yes. Questions? Okay. So there is a little problem. Yes.
Could we look at, so in this case, so we're the example that you have age less than equal 30, income medium, student yes, credit rating fair. We're basing it on that probability and sort of multiplying it, assuming they're independent events.
Yes.
Is this similar to what one does for the the chi-square, those contingency tables, to, or am I overthinking that?
Right, in chi-square contingency table, we compute there is definitely similarity. We compute the expected value by applying this independence assumption. That's how we get to the expected value. Then we can see how far away the observed value is to the expected value. So naive Bayesian has one little thing is, as we can see, this score is a product of many elements. Any of the elements taking a value of 0 will result in the final probability of being 0. This would occur when the training example does not cover something that's in a new example. So assuming that we have in our training data set, we have 1,000 tuples. We have high and medium income, but we didn't have low. Yet our new example that need to be classified actually have somebody who's low income. Then we will not be able to estimate this conditional probability element for this classification task, because the prior the income for this class low for buying or not buying, this income is actually 0. So it will create 0 values in this in some terms in this equation. In order to avoid this problem, we can use Laplacian correction, also called Laplace estimator. Idea is very, very simple, just to add one. We just need to have a very small probability value to make sure this term is not 0. So because we have income have 3 levels, we need to add to the denominator 3. So they add up together to be 1. So this is a way to avoid having 0 probability computation in naive Bayesian. Questions?
So is that a case where, like, to use an example, like if we were in the previous thing, suppose we got a credit rating that is, right now we see fair and excellent. So suppose we got a credit rating of unknown, then we don't know it. So,
yeah.
Okay.
Exactly. Yeah. Right. That's a good observation. It could also occur when we do 10 cross validation. The sample, the training split does not have certain thing represented in the test split. You will not be able to correctly estimate your model performance in those scenarios too. So this Laplacian correction, although very simple, but it's totally useful.
So if we have this after the Laplacian correction, how does it decide what class for example, here low income is, because it doesn't have any samples to train on?
Right, exactly. So it will end up to have a very, very, so we're assuming, so this is a good assumption, right? Because I think in any case, any rare event would happen. It will only happen with a very, very low probability. So this adding 1 meant to model this real scenario in any type of situation. Anything that has not been observed, probably going to have a very, very low probability. Very simple, we could go out our way to build another model to estimate this probability. But we could also use the simple Laplacian correction to just plug in 1 to solve this problem.
Yeah, I mean, this makes sense, but how do you estimate what class that one should belong to, or when we encounter it, how do we classify this?
It's again following exactly the same thing.
But we don't have a sample to use to decide where
we
to
don't,
put it in.
yes. We don't have a sample to estimate. Therefore, we just put a very, very small number there.
So do we assume that?
Yeah, we assume it has a very low
probability. Belongs to both classes?
Right. So if buying this has 1,000 tuples, let's say not buying has 100 tuples, then the conditional probability of income equals low, buy equals not would be 1 over 103. That will give us all the information we need to compute this, to decide. I understand your question is, we don't have training example to estimate this. This is why we give a fixed low probability to solve this problem. Once we have this given low probability, that then we can follow exactly the same steps to predict, to see which class this low attribute is more likely to happen.
So in this case, um, the so we have 1,000 tuples total, but
We're
then
saying by has 1,000 tuples.
oh,
Sorry.
by has 1,000 tuples. Okay, and then not by has so by with 1,000 tuples 990. Sorry, I'm confused. How many are like in the computer by a yes versus no? Like the predicted class. What is the size of each?
Sorry, I changed from our previous example to illustrate this idea of being a very small probability. In this example, we can say that buying has 1,000 tuples. Most people are going to buy a computer. Not buying 100 tuples.
Okay, so by is 1,000, 1,000, not by is 100. So then in this new tuple, like I guess I got confused of how the denominator becomes 1,003.
It's 100 and sorry, because as you can see, all those three adds together need to be 1.
Oh, so we add not 1 just to the, like it's not like we now have 1,001 tuples. We have 1,003 tuples because.
Exactly, yes, because every one of them added 1.
Originally, low income is yes, medium is 990, and high is 10. So 1 is added to each of them.
Yes. Because it would not be fair to just add 1 to low. We add 1 to all of them, and that makes our denominators increased by 3. But we make sure this scheme will give us all those 3 probability adding up together. See, this is the total buying probability, no matter what income is. This 3 thing adds up to be 1. So we still have a probability distribution. So another way of looking at it, in order to give a low probability, this schema allows us to give a very low probability to this unobserved value, while still keeping a probability distribution for this class, for this conditional distribution.
And what about for the no, like right now it says by is equal to yes. So do we do the same thing for by equal to no? Like
Yes.
Okay, so sorry.
Right. If in the no group, we still don't have low income. Maybe in the no buying group, we have low income. In that case, we don't need to do anything.
Okay, so if it's already there in the like the opposite class, like if this is, let's say the first class is by, it's not here, then we add it for each income level. But then if it's there in the other class, we don't have to do anything. But if it's not there in the other class, we have to repeat the same thing in the other class and add it.
Exactly.
For
yes.
that as well.
Yes.
And I see. Now, what is the like when in earlier in the semester when you talked about missing data, you said one of the option is so like sorry, let me backtrack. So in this case, let's say this is a new row with new data that we didn't have before. What about if we built a model that excluded income and predicted based on that decision tree? Is that better, or is it better to do this in terms of the quality of result?
Can you see that again? Sorry.
So suppose we have, like in the previous example with the computer buyers, we had 4 attributes that were used to predict the computer buyer.
Yeah.
So assuming in this data set also we had 4 attributes and income is one of those 4 attributes. Now, I guess the question, so I was wondering that in practice, which is better? Should we use a model that only uses 3 attributes without the income, or should?
No, I will definitely, the zero probability problem will not in effect hurt the performance that greatly. I will not, because of lacking certain values to purely based on this to choose a different model. No. What I hear you saying that since income does not give us complete information, we cannot reliably using the training example to estimate its distribution. Maybe we should just drop income completely.
So, well, sorry, I guess I was not clear. I was thinking like whether we should, let's say there's certain number of data points, if they are significant. One option is, of course, to throw away the data point, right? As you said, when you have missing data, one option is just throw away the data point, saying, okay, this data point is null value or just weird outlier, throw it away. I guess the other option then is, one is of course this option, and then perhaps a third option is, as you were saying, to build 2 separate models. In one model, we are looking at those data points that have just high and medium, and then in another model, we look at the ones that, where essentially we build a separate model that does to handle these outliers or some small number of, because I'm assuming this new value is an outlier, new observation is an outlier of some sort.
I don't think so. This I'm not sure this is a missing data. It's missing observation. It's not certain observation has a piece of data that's missing. It's more like missing an entire observation or training data being incomplete. But in a lot of data mining, data mining applications probably is less severe. Like you don't have enough training examples. Most likely you have lots of training examples. But in general, in machine learning algorithm, most of the problem, we do not have enough training example. Recall we talked about the curse of dimensionality. When you have lots of attributes, then you need different combinations of those attribute values in order to learn a phenomena. This is example when you don't have enough training example to model certain, you don't have enough training data per attributes to learn or model a phenomena. This problem occurs for almost every, it's a common problem. It's not specific to naive Bayesian classifier, only because we have to compute this conditional probability. This becomes the issue that can be easily solved using Laplacian. Maybe we can discuss more on this later.
Thank you.
Yeah, sure. So we can actually, yeah. So this classifier, naive Bayes classifier, naive Bayesian classifier, I use those terms interchangeably. Sorry about that. If that's confusing to you, but you know what I meant is the same thing. So the algorithm obviously is very, very simple to implement. You actually don't need to actually build the model. You just need keep on adding your training examples. The prediction may change or improve. The disadvantage, the major thing is the class conditional independence. Lots of applications that use naive Bayes does not meet this assumption, but they also, even when they don't meet the assumption, they often give very good results. So nobody cares about this conditional independence assumption anymore. Nobody checks it. We just use it and see how it performs. So the dependencies obviously exist among those variables, even when class is known, because class label is all given, right? You can provide whatever class label that you want. That really doesn't add any information. It's not the age that adds that remove the dependency between children's height and their vocabulary. And so there are other ways to address this. We're going to look at Bayesian belief network in the next chapter that actually models precisely the dependencies. However, even in those Bayesian belief networks, we also need other assumptions to simplify the computation. Only the dependencies, the assumption is less severe. I mean, it's less strong.
So in this case, the reason we would not do like a PCA to get things that are independent, is that because if we do that, the attributes don't have the meaning that we can interpret the model with?
Right, that's one of the major things. And also really because even when you don't have those assumptions, I mean, even if the assumption is violated, you still get good performance. Then why do I have to spend that effort to construct other models if we end up to be having a good, useful model? Naive Bayesian classifier before support vector machines is one of the dominant text classification algorithm. It's routinely performed at 85% and above accuracy, precision, and recall. So for practical purposes, those are good enough. That's why it's very popular at that time. And then support vector machine was invented, and then people realized support vector machine gives much better performance, and it did. Support vector machine then becomes the predominant algorithms for text classification and many other classification problems, and it's still very, very useful, even with deep neural network when you don't have enough data set. Training examples like support vector machines, other methods are still very, very useful.